Hello guys, this is yet another problem from Atcoder's educational DB contest, which was held in 2019, and this problem number E, and this is again knapsack based problem. If you remember, I have already done a video on knapsack 1, which was this problem. So the problem statement here is very much similar, only difference here would be the input will be having different constraints here. So let me just read through the problem statement again. So we are given n items which are numbered from 1 to n, and each item has some weight and a value assigned to it. Now Taro has decided to choose some of these n items and carry them home in a knapsack. The capacity of the knapsack is given to be W, which means that the sum of the weights of the item that he picks should not be more than W. What's the maximum possible sum sum of the values that Taro can take home? So this is very much similar to this problem statement, exactly same. Here here let's talk about the current problem for now. Here what are we given is the number of items can be 100 only, and the weight of the knapsack can range from 1 to 10 raised to power 9, and each item's weight can also range from 1 to 10 raised to power 9, and the value can range from 1 to 10 raised to power 3. So if you see, the difference here is that the value here would range from 1 to 10 raised to power 9. However, the weight was restricted to be below 10 raised to power 5. So if you remember our approach here, let me just quickly open my submissions and walk you through the knapsack code. So as you can see here, what we did is we solved this recursively and then also memoized this sub problems, because the sub problems here were overlapping. And what we did is for each item we were checking, for each item we had two options: either include it or not include it into the knapsack. So if we don't include it, we just iterate to the next one, and we keep one more weight, a parameter, to keep track of how much of items that we have already taken till now. And then if we are going to include it, then we'll check whether this particular weight of this item plus the overall weight that till now is less than or equals to W, which is the capacity of the knapsack. Then only we will include it. So basically we were also using a DP table of 109 cross 10 raised to power 5 plus 9, and this was used to store the previous calculated result, like all these unique states of this recursion. And here, as you can sense, that this weight can range from 0 to the weight of the capacity of the knapsack, which would be, in our case, it can go from 1 to 10 raised to power 9. So first thing that we can notice is we cannot memoize this. We cannot make this big table into our program. And the second thing, even if we were able to make such big size of DP table, our program here, because the time complexity of the program here is the number of items multiplied by the overall capacity of the knapsack. So this would definitely time out, because in our case the number of items are 100 and W is 10 raised to power 9, that is 1 billion. So overall 100 billion operations are done, and this is going to time out because the time limit is given to be 2 seconds. And of course the memory limit was anyway going to time out. Memory limit is also going to exceed. Also the time limit is also going to exceed, because it will take 100 billion operations, and in 1 second most of the engines are doing around 100 million operations. So so now I think we understand that why this approach wouldn't work here, that we can iterate over each ID and keep a track of the weight of the weight that we have taken till now. So now let's try to understand how can we approach it, what are the difference in the algorithms that we are going to take in case of knapsack, where the knapsack size is way bigger and the value is smaller. And this value is something which gives us a hint about what else we can do. So here we can think of trying to do something around the values instead of doing around the weight that we were doing previously. So what we can do, so as we can see, that what can be the at most value that we can get here. So number of items are 100, so let's say even if all the items are given the maximum value, that is 10 raised to the power 3, so the maximum value that we can achieve would be from 1 to 10 raised to the power 5. Alright, so in general what we can do, we can find the maximum value that we can gain by adding all the values of the items that are given to us. And let's say we find some Vmax, that is what the maximum value that we can achieve. Then what else we are supposed to do with that maximum value? We will try to see that how much weight is required if we were to gain this much amount of value, and we will then find out what's the maximum amount of weight that we will need. And if that weight is below the capacity of the knapsack, that means we can pick that one and we can simply return that this is the maximum amount of value that we can gain. Otherwise, what are we going to do? We are going to decrease our value by 1 and we are going to check for this new value, and hence we can just linearly scan through all the values possible from Vmax till 1. Vmax is the total amount of values, the sum of the total values that we have, and till 1 we can just traverse and see if there is any W which is less than, if there is any weight for any of these values which is less than W, so that will be our that particular amount of sum will be our answer. And why this would work is because we are traversing from the other side, like from Vmax till 1, so that will ensure that this is the maximum value that we can gain if at any moment we find some weight which is below the knapsack capacity. So now our main problem is transformed into a different problem where we are supposed to find a minimum weight required to gain a certain amount of value, and then we can iterate over each value and see which one is getting us the most optimal answer. And this problem is also very much similar to what we have done in case of the regular knapsack. So instead of passing a weight that we have till now, we will need to pass into our function a value that we are aiming for. So most of the functionality is very much similar, so I'll just walk you through the code. And what here I'm doing is I have taken out the overall sum of the values that I have, and this would be our maximum value that we can achieve. Then I'm trying to call the maximum amount of sum that we can get by using this function, and I'm iterating from Vmax till 0 and checking if any of this value for within this range Vmax to 0 is below the weight of the capacity. That means if at any moment we have seen a certain amount of value that we can gain within the capacity, then we can simply return that value. Otherwise, in the end we will return 0. That means we can't get this is the least amount that we can get, least amount of value that we can get. So now let's say, for example, we send this I as Vmax itself. That means what's the minimum amount of weight that will require to gain this Vmax amount of value, and this R is telling us the amount of remaining values. So initially this would be equals to the amount of maximum for Vmax, and then we are just doing this regular recursive function where I'm checking if there is no items left, then I should not have any remaining values left as well. If this is the case, then yeah, the total weight required would be 0. Otherwise this is an invalid scenario, and because we were to give back the minimum amount of weight required here, if it is invalid, we will try to give some big amount of value. And again, for every item we have two options, whether to include it into our knapsack or not. So in case we can just in case when we are going to skip it, that is not included, we can simply keep the remaining values to be same and go to the next item. And otherwise, when we are going to include this item, we will check whether the value required, B is representing the values for each item. So the value for this item is below the remaining value that we have, and if it is, then is below or equals to. So in that case, we would compare this answer with the option that we had chosen previously, and if that is the case, we will add the amount of some amount of weight that we are gonna add into our knapsack, and then we are going to just decrease, because we said that we are going to lose this much amount of value from the remaining values. So we'll decrease it and we'll go to the next item. And because this will also be very much similar, and these subproblems are overlapping, so we are going to memoize this, and memoization is possible here because the remaining values can be as big as the Vmax, and Vmax, as we have seen by doing the initial calculation, that it can go from 1 to 10 raised to power 5 only. So we can memoize it as well, and here that's what I'm doing. If this state is already calculated, I am returning that value, otherwise I am calculating and memoizing it. So yeah, the time complexity for this one is changed to O of n into V, where V would be the maximum amount of values that we can have in a given array. And yeah, this runs, and as you can see, it has already passed all the test cases. So I hope it was helpful and I was able to explain you guys. And if there is any comment or any feedback or suggestions for me, please leave in the comment section. I'll also give the code in the description, the link for the code. And yeah, please watch my other videos from this educational DP contest series, and I hope it will be helpful for each of us. And yeah, if there is any feedback from me, as I said, please leave it in the comment section, or if any recommendation for any other video that you have, please let me know. And thanks for watching this video, guys.